It's time for fun with math, and we're back with part two of the law of sines and cosines, and we're going to concentrate on here on the law of cosines. And so the law of cosines is a formula that's sort of like a generalization, if you like, of the Pythagorean theorem. And again, it works for any triangle, not just a right triangle. You can see kind of the part of the Pythagorean theorem here, a squared plus b squared equals c squared. And to generalize it to any triangle over here, you have this sort of like correction term, minus 2ab cosine of c. There is sort of a word of warning. This is one of really three formulas. You can actually swap out a, b, and c and get two other formulas. So for example, instead of c squared here, you could actually have a squared equal to b squared plus c squared minus 2bc, and then cosine, instead of the angle c, you have, of course, the angle a. Or you could start with b squared here, and then this is going to be equal to a squared plus c squared minus 2ac, and then the cosine of angle b. But in general, we just write down this one formula, knowing that we could, have these other two formulas here found from this one. All right, so let's talk about why this formula is actually true. So here, the law of cosines, here's the formula. And to prove this, to show where it actually comes from, we start with this sort of general triangle here. And remember, all we really know are things about right triangles. So our idea is just to take this triangle here and somehow turn it into a right triangle. In this instance, just like before with the law of sines, we just drop down a perpendicular, and we're going to give this a name. I'm going to call this height z, and of course this turns the general triangle that we had into two different right triangles. And what we can do then is we can use the Pythagorean theorem here. We're going to call this x and this y. And I'm trying to use this Pythagorean theorem because I'm trying to introduce these sort of squares in here. So what you'll notice is that for this triangle, we're going to have c squared is equal to x squared plus z squared. It's where x squared is this distance from here to here. So this is equal to x squared plus z squared. And over here, we know that we can use this right triangle, and we can show that we also have a squared, which is the hypotenuse of this right triangle here, is equal to y squared plus z squared. So this is just following from the Pythagorean theorem with these two different right triangles. Now, what we want to do is we know what the formula should look like, which you can actually find by experimenting with triangles. And so what we could do here, though, is we can bring this sort of a squared into this equation by solving this one here for z squared. So let's do that. So this implies that z squared is equal to a squared minus y squared. So we just subtract y squared from both sides. And then what we can do is we can plug into the first equation for z squared. Since z squared is this, we just replace it with what it's equal to here. So we're going to get c squared is equal to x squared plus, and then z squared was a squared minus y squared. All right, so we're getting closer to the formula that we want. So what we can do next is we have actually down here a relationship between x and y. We actually know that this b is equal to x plus y. So what we can do is we can solve this for x, if you like, and plug in over here, and that's going to introduce a b squared into our term. So let's see here. So let's solve this for y. So y is equal to, and we have b minus x. And so now, wherever I see this, oh, sorry, I meant to solve it for x. Let's solve this for x. So this implies we're going to solve this for x. So x is equal to this b minus y. The reason you kind of want to solve this for x is that, if you plug it in here for x, you actually get rid of all the x stuff and you'll be left with just b and y stuff. So now let's plug in. So here's my x right here, and I'm going to replace that with my b minus y. So I get c squared equal to b minus y quantity squared plus an a squared minus a y squared. And so we're going to multiply this out. We're just going to multiply out that b minus y squared, which remember is b minus y times b minus y. So when you FOIL this out, first, outer, inner, last, what's going to happen is we're going to get that c squared equal to, we'll get a b squared here, a minus 2by, that middle term, plus a y squared, and then we'll have plus our a squared and minus our y squared. And so these y squareds are going to cancel, which leaves us with what? Which leaves us with this c squared equal to, I'm going to kind of rearrange the terms. So I'm going to write a squared first, so I have a squared, and then plus a b squared, and then minus a 2by. And what you'll notice is we're almost to our sort of formula here. So our formula is a squared plus b squared, so we have a squared plus b squared, and then minus a 2, and then we have a b, we're just missing an a cosine of c. But what you'll notice is if you look back in the picture at y, so here's y right here, if you write down what the cosine of c is, the cosine of angle c is the adjacent over the hypotenuse, so it's equal to y over a. And if we multiply both sides by a, it tells us that y is actually equal to a cosine of c. And so what we can do now is we can plug this in for our y, because it's what it's equal to, and we get the law of cosine. So c squared is going to equal a squared plus b squared, and then minus a 2 times b, and then y, of course, was that a cosine of c. It's a cosine of c there. And you can just rewrite this if you like. So, c squared is equal to a squared plus b squared minus 2ab, just right into the ba, right, ab, and of course cosine c, and that's the law of cosines. Now I don't expect you to memorize this procedure by any means, but what I want you to remember from it is that how do you derive this formula from a general triangle? Well, you split it up into two right triangles, and it's a generalization of this sort of Pythagorean theorem that we've been using all the time here, where that's a, that's b, and that's c. We have a squared plus b squared is equal to c squared. But this formula works here for any triangle, not just right triangles. All right, let's do a problem with this one. It's kind of a tough one. So in this problem, we want to solve the triangle. They give us all three sides. So the idea is what we really want to do is we want to find this sort of angle A and B and C. So that's what we're looking for, these three sort of angles here. So sort of our picture. And to do it, we're going to use that law of cosines. And so let's write down the law of cosines, and we'll just use it. So we know that c squared is equal to a squared plus b squared, and then minus that 2ab cosine of c. And so we know certain things. We know all the little a, little b, and little c, and we just need to find that angle c. So let's just plug and chug basically. So here you're going to get 10 squared is equal to, and a is 8, so 8 squared, plus b is 10, so 10 squared, minus 2 times 8 times 10, and then cosine of c, so this is just basically 100, and that's equal to, then this is what, 64 plus 100, so 164, minus 2 times 8 is 16, times 10 is 160, and then we have cosine of c. And so now we can solve this basically. We'll start solving this equation to find what cosine of c is. So we'll subtract 164 from both sides and get negative 64 equals a negative 160 of cosine of c. Then we're going to divide out by this negative 160 on both sides. And then what happens is we get the cosine of c equal to, on this side the negatives cancel and you have 64 over 60, but of course those are both even. So it's actually what, 32 over what, 80, and then that's actually 16 over 40. So we just keep on reducing by 2. So 8 over 20, right? Keep on going. So 4 over 10, and then finally 2/5. All right, so what this tells us then is that the cosine of the angle, the cosine of c, is simply equal to 2/5. And so in order to find what c is, we'll take the cosine inverse of both sides. So c is equal to cosine inverse of 2 over 5. And if we want to know this in terms of degrees, we can use our calculator. So take out your calculator. Make sure you're in degree mode. So I'm in degree mode, so I'm good. And so we can take the second cosine of 2 divided by 5, so cosine inverse of 2/5, which will be equal to about 66.4 degrees. So here we can say that this is about 66.4 degrees. So that's my angle C up here. It's about 66.4 degrees. Now, because this is an isosceles triangle, we could actually say that this side here should be exactly the same, because this is 10 and 10, so this should probably also be 66.4 degrees. And since we know that all the angles need to add up to 180 degrees, we know that this angle right here should be what? It should be 180, should be about 180 minus 66.4, and minus another 66.4, and we get our answer here of about 47.2 degrees. So here we can write 47.2 degrees. Now, if we wanted to know this angle exactly and not approximately, we would have to do the law of cosines again. But now, this time when we did the law of cosines, we would use a different formula. Since we're using angle A, we're looking for angle A right here, we would have a formula starting with a squared. So we'd use this formula. A squared is equal to b squared plus c squared minus 2bc, and then cosine of angle A. And we basically would do exactly the same thing that we did before. All right, so here for A, we plug in 8, and so we have 8 squared equal to, and if we plug in B here, which is 10 squared, and then plus C, which is also 10 squared, minus 2 times 10 times 10, and cosine of angle A. And we would get 64 equal to 100 plus 100, which is 200, minus 2 times 10 times 10, which is 200, and cosine of A. We subtract 200 from both sides and get negative 136 on the left equal to negative 200 cosine of A on the right. Then just simply divide out by negative 200 on both sides. And then what would happen? We'd have the cosine of A on the right, and on the left, this would equal, the negatives would cancel. And again, these are both even, so this one would be what, 68 on top if you reduce the 2's over 100, right? Because 68 times 2 is what, 120, and 16, which is 136. That works. These are still divisible by 2, so this would be what, 34 over 50, and then finally I think it would reduce to 17 over 25, and then we simply have cosine of A equal to 17 over 25, and we can take the cosine inverse of both sides. So this implies that A will equal the cosine inverse of 17 over 25, if we didn't make any silly algebra errors. And we can check this on our calculator to see if it is indeed about 47.2. And so we have second cosine of 17 divided by 25. And it checks out. So it's about 47.2 degrees. So I'll write that down. It's about 47.2 degrees. So angle A is exactly cosine inverse of 17 over 25. Angle C is exactly cosine inverse of 2/5. Of course, angle B is exactly the same as angle C because this is an isosceles triangle. These two sides are exactly the same. So if you want to know exactly what angle B is, it would be cosine inverse of 2/5, which is approximately, again, 66.4 degrees. So we have our answers here for angle B, C, and finally for angle A. Let's move on and let's do a word problem now. And so in this problem, we want to find the distance from the house at A to the house at B. So we're looking for this distance from here to here. If you like, we could call this C. A surveyor measures an angle ACB to be 60 degrees and then walks the distance to each house of 40 and 50 feet. So they did this 40 feet and 50 feet. How far apart are the houses? So this is sort of my picture, which is nice that they give it to me. And I want to find C. And so to find C, I'm going to use that law of cosines. So it's going to be C squared equals A squared plus B squared minus 2AB cosine of C. And it's really sort of just a plug and chug. So C squared is going to equal, and so A, let's let, this side is A, so 50 squared plus 40 squared. So 50 squared plus 40 squared. And then minus 2 times 50 times 40. And then cosine of the angle is 60 degrees, so cosine of 60 degrees. And so C squared is going to equal. It always helps to show a little bit of work while you're doing these problems. So if you like, I would show a little work here. That way if you make a mistake, you can still get some credit. So what I have is 2,500. Right here is 2,500 plus 40 squared should be 1,600, and then minus. So then we can check that just to make sure I didn't make a silly mistake. So 16 squared there, which is, oh sorry, not 16 squared. So 40 squared, which is 1,600. That's good. So then 2 times 50 times 40. So 2 times 50 times 40 is equal to 4,000. So we can write 4,000 there. So I have 4,000. And then cosine of 60 degrees. And so what does that leave us with? So C squared is equal to, so I have 3,000 plus 500 and 600, so 1,100. So 4,100 minus 4,000 cosine of 60 degrees. And so now it's time for me to sort of, and I know the cosine of 60 degrees. Cosine of 60 degrees is actually root 3 over 2. So it's not going to be a nice number, so I'm just going to write this down. So 60 squared is going to be, I'm actually going to write C is going to be equal to, so remember this is C squared, so C is going to actually equal the square root of what? Oh, this is better than I thought. This is not root 3 over 2. All right, what's 60 degrees? So cosine of 60 degrees is actually 1/2. That's nice. All right, so let's remind us of this table that we have here. So we have 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And so if I want to do cosine of theta, remember this one is 1, so it goes root 4, root 3, root 2, root 1, and root 0. These are all divided by 2. And so now I see that this is actually a much nicer number than I thought it was in before. And so cosine of 60 degrees is 1/2. And so I can actually show that this is going to be C squared is equal to 4,100 minus, and 4,000 times 1/2 is 2,000. And of course then C squared is equal to 4,100 minus 2,000 should be 2,100. And then we can take the square root of both sides. So C is going to be equal to the square root of 2,100, which you actually can write that as, simplify that a little bit, because that's 100 times 21, and the square root of 100 is actually 10. So that's actually 10 root 21, and this would be feet. So that's my final answer. And then if I want to approximate this, you could approximate this on your calculator. So this would be approximately, and then do 10 second square root of 21, and you'll see you get out about 45.8 feet. So down here we could write this is about 45.8 feet. Right, but my answer is actually 10 square root 21 feet because that's exact. All right, so that's what ends this two-part video on the law of sines and the law of cosines. Remember, this formula can be written in two other ways, and so a lot of times when I use it, I'm not so much memorizing the formula as I am, well, when does this formula actually work? Well, if you know this side, and this angle, this is going to allow you to calculate this distance here. So that's kind of the setup that we have typically. If you look at this last problem, the typical setup is you know two sides and an angle, and you can find out the other side using the law of cosines.